Picture the Mediterranean Sea 2,000 years ago, not as a calm, blue postcard, but as the bustling, chaotic heart of the known world. The air is thick with the smell of salt, tar, and sweat. The sound is a constant roar of crashing waves, shouting sailors, and the rhythmic, groaning creak of wood under immense strain. And on that horizon, appearing first as a speck, then as a terrifying silhouette, is the true engine of an empire, a Roman warship. A trireme powered by 3 tiers of oarsmen, its bronze-covered ram glinting in the sun, a floating fortress designed for one brutal purpose, absolute domination. Now hold that powerful image in your mind, because we are about to tackle one of history's most captivating engineering mysteries. How in the world did they build that? We live in an age of meticulous planning. To construct anything of significance, from a skyscraper to a simple piece of furniture, we rely on intricate blueprints, digital models, and precise measurements down to the fraction of a millimeter. We have instruction manuals for everything. The Romans, however, left behind almost nothing of the sort for their ships. No detailed plans etched on papyrus or carved into stone. No massive shipyard manuals survive. And yet, they didn't just build a few boats. They constructed a naval empire, producing vessels of stunning complexity and scale with a consistency that feels almost impossible. This is the great paradox of Roman shipbuilding. We can stand in awe of the Colosseum, we can walk the roads they paved, but their greatest vehicles of power, the ships that connected and controlled their world, seem to have been built by a kind of magic. The secrets of their construction appear to have vanished beneath the waves of time. But what if those secrets weren't lost? What if they were just written in a different language? A language not of ink and paper, but of wood grain and hand tools, of practiced skill and brilliant organization. This video is a journey to decode that language. We are going to step into the noisy, sawdust-filled world of a Roman shipyard. We will meet the master shipwrights, the unsung geniuses who could look at a stack of raw timber and see the skeleton of a warship. We will uncover the ingenious, almost intuitive techniques they used to achieve such breathtaking precision without a single blueprint as we know it. This is a story about more than just nails and planks. It's a story about a system, a mindset, a level of human ingenuity that allowed an entire civilization to master the sea and shape the course of history. Get ready to see ancient Rome in a whole new light, from the waterline up. To truly appreciate the genius of their methods, you have to wrap your mind around the sheer, staggering ambition of their maritime empire. This wasn't a hobby or a small coastal operation. It was a full-blown industrial enterprise on a scale that would be impressive, even with today's technology. Think about the diversity of their fleet. It wasn't just the famous triremes. They built the mighty quinquiremes, even larger warships powered by 5 banks of oarsmen, each one a floating siege engine. They constructed the corbetters, the massive, round-hulled merchant ships that were the 18-wheelers of the ancient world, carrying grain from Egypt to feed the million inhabitants of Rome. And then there were the specialized vessels, swift Liburnians for scouting and raiding, sturdy transports for moving legions and their equipment, even elaborate pleasure barges for the elite. This wasn't a one-size-fits-all operation. It was a navy and a merchant marine tailored for every conceivable purpose. But the real mind-bending part is the volume. During the First Punic War, a conflict fought largely at sea, the Romans faced a crisis. They lost almost an entire fleet in a storm. A lesser power would have been broken. What did Rome do? According to the historians, They built a new fleet of 200 warships from scratch in just 3 months. Let that number sink in. 200 complex, oar-powered warships in 90 days. That's more than 2 ships launched every single day. This single fact reveals a shipbuilding machine operating at a fever pitch. A process so refined and so well organized that it defies belief. Now consider the logistics behind just one of those ships. A single quinquereme required acres of ancient forest. Tall, straight trees for the keel and the massive mast. Curved timbers for the ribs. It needed tons of metal for the deadly bronze ram, and for the thousands of nails and fastenings that held it all together. It consumed hectares of flax or hemp for the sails, and the miles of rope needed for the rigging. And most importantly, it demanded a small army of highly skilled workers. Lumberjacks, carpenters, blacksmiths, rope makers, sail makers, and the master shipwrights who orchestrated it all. Multiply that by 200, and then imagine coordinating that effort across multiple shipyards, all while a war is raging. This wasn't just carpentry. It was the peak of ancient industrial logistics, a symphony of coordinated effort that had to function with breathtaking speed and precision, all without a single central blueprint office, as we would recognize it today. This immense pressure is exactly what forced the Romans to develop a system that was not just effective, but revolutionary. So we're left with this glaring void in the historical record. We have stone inscriptions detailing tax laws. We have intricate scrolls on agriculture and architecture. We even have personal letters and shopping lists preserved by chance. But for the plans of the very vessels that built and sustained the empire, we find almost nothing. This is the great silence at the heart of our mystery. Why would such a meticulous, record-keeping civilization leave the instructions for one of its most critical military and economic assets so completely unrecorded? The most straightforward explanation is one of simple material fragility. Think about what a blueprint would have been made on in the ancient world. It wouldn't have been a large, durable sheet of parchment reserved for important documents. That was far too expensive. More likely, a shipwright would have used something temporary and reusable. A wax tablet, perhaps, where lines could be scratched to map out the curve of a hull, then smoothed away for the next design. Or maybe drawings were made in charcoal on a flat wooden board, or even sketched directly on a cleared patch of earth or sand in the shipyard itself. These were working documents, not meant for a library. They were practical, ephemeral tools that lived and died with the construction project. When the ship was launched, the blueprint was erased. The real plan was the ship itself. But the mystery deepens when we consider that even written accounts from the time are strangely silent on the specifics. Roman authors like Vitruvius wrote entire volumes on architecture, explaining the principles of building temples and aqueducts in great detail. Yet no comparable manual on shipbuilding survives, if one was ever widely circulated at all. This suggests something more than just perishable materials. It points to the idea that this knowledge was not considered public information. It was a trade secret, a fiercely guarded craft. A master shipwright, a navicularius, held the power of this knowledge. His expertise was his livelihood and his reputation. It was a form of intellectual property, passed down carefully from master to apprentice, from father to son, through years of hands-on training. You didn't learn shipbuilding from a book. You learned it by feeling the wood, by swinging the adze, by absorbing the unwritten rules and proportions that defined a seaworthy vessel. This system of oral tradition and practical apprenticeship might seem haphazard to us, but it was incredibly robust within its context. The knowledge was stored not on papyrus, but in the minds and muscles of the craftsmen. It was a living library of technique. This also explains the remarkable consistency we see in Roman shipwrecks found across the Mediterranean. Even though ships were built in different yards, often centuries apart, by different crews, their fundamental proportions and construction methods are strikingly similar. This wasn't achieved because everyone was working from the same central drawing, but because everyone was trained in the same school of thought, the same set of proven principles. The blueprint was a mental template, a shared understanding of what made a Roman ship a Roman ship. The secret wasn't lost. It was simply woven into the very fabric of their culture, a masterpiece of engineering hidden in plain sight, communicated through the skilled hands of generations of builders. This individual, the Navalis architectus, was the absolute cornerstone of the entire operation. Think of him not as a simple foreman with a hammer, but as the conductor of a complex and dangerous orchestra. He was an engineer without a formal degree, a designer without a computer-aided design program, and a project manager responsible for a massive budget and an unforgiving deadline, all rolled into one. His authority came not from a scroll of official qualifications, but from a deep, almost instinctual knowledge that had been passed down to him, honed over a lifetime of working with wood and water. He was, in the most literal sense, the living, breathing blueprint for the ship. His expertise was entirely empirical. This means it was based on direct observation, practical experience, and proven results, not on theoretical calculations. He learned his craft not in a classroom, but by starting as an apprentice, probably as a young boy, fetching tools and watching intently. He would have learned by doing, by making mistakes on smaller projects, and by absorbing the unwritten codes of his trade. Over decades, he built up a mental library of what worked and what didn't. He knew that a keel made from a particular type of oak had the perfect combination of strength and flexibility to withstand the pounding of the waves. He understood exactly how to season timber so it wouldn't warp disastrously after the ship was launched. This knowledge was his most valuable possession, his intellectual property, and it gave him immense power and respect. At the core of his design philosophy were these rules of thumb, simple, proportional systems that guaranteed a harmonious and seaworthy vessel. He didn't work with precise feet and inches, but with ratios and relationships. For example, the primary rule might have been something like this. The length of the keel should be 4 times the ship's maximum beam, or width. Once that keel was laid, every other part of the ship was determined in relation to it. The rise of the stem and sternpost, the curve of the hull frames, the placement of the mast, all of these were dictated by a set of proportional rules that were memorized and applied with remarkable consistency. This is the real secret to how they could build so many ships so quickly, and have them all perform identically. They weren't copying a drawing, they were all applying the same recipe. The master shipwright held this recipe in his head. He also possessed a fundamental, almost intuitive grasp of hydrodynamics, the way water moves around a hull. He knew that a slightly rounded bottom allowed a ship to ride over the waves with more stability, while a sharper entry at the bow helped it cut through the water with less resistance. He understood how to distribute the weight of the ballast stones in the hold to keep the ship from capsizing, yet allow it to be nimble enough for combat maneuvers. This knowledge came from watching ships he built succeed or fail. When a ship returned from a long voyage riding perfectly, he knew his proportions were correct. When one was sluggish and difficult to steer, he mentally adjusted the ratios for the next build. It was a continuous process of refinement based on real-world performance. As for his social status, the Navalis architectus occupied a fascinating and crucial position in Roman society. He was undoubtedly a man of significant standing, commanding high wages and the respect of even military commanders and wealthy merchants. His success directly impacted the security of the empire and the flow of commerce. A mistake in his design could mean the loss of a warship, its crew, and a crucial battle. A well-built merchant vessel meant profits for its owners and grain for the city of Rome. This responsibility placed him in a unique category, a highly skilled artisan who was essential to the state's power. He wasn't a patrician sipping wine on a balcony, but he was far more than a common laborer. He was a technical expert whose skills were in constant, desperate demand. Directing the large teams of workers required a blend of sharp vision and clear communication. Imagine the scene in the shipyard, a cacophony of saws, hammers, and shouts, with hundreds of men specialized in different tasks. The master shipwright would have moved through this organized chaos, overseeing every critical stage. He wouldn't need to micromanage every nail. Instead, he would establish key reference points. He might have had a master mold, a full-scale wooden pattern for the most important frame of the ship. Once that central frame was correctly positioned on the keel, his teams of carpenters could then build the rest of the frames forward and aft using a set of predetermined spacing rules, known as the harmonic series, where the space between each frame decreased in a specific pattern. The shipwright's job was to ensure that this skeleton was true and fair. He was the one who would run his hand along the emerging hull, feeling for any deviations from the perfect, sweeping curve he envisioned. His word was final, his eye unerring, and the entire project relied on his ability to hold the complete, finished ship in his mind long before the first plank was ever steamed and bent into place. This brings us to the brilliant organizational principle that made such rapid construction possible, the ancient world's version of mass production. While they weren't assembling ships on a conveyor belt, the Romans perfected a system of standardization and modular design that eliminated the need to reinvent the wheel with every new vessel. Think of it not as building a custom mansion from scratch each time, but as using a set of well-understood, interchangeable parts to construct a highly effective and replicable structure. The very names of their ships, trireme, quinquereme, Liburnian, were more than just labels. They were detailed technical specifications in a single word. When a Roman admiral ordered a fleet of triremes, the shipwrights knew exactly what that meant. They had a shared mental template for the ship's length, its beam, the number of oarsmen, and its overall performance characteristics. This shared understanding was the foundation of their entire shipbuilding enterprise. This standardized typology allowed for a truly modular approach to construction. Instead of crafting each component as a unique piece for a specific ship, workshops could pre-fabricate parts to standard sizes. Picture specialized teams working in parallel, not in sequence. In one part of the shipyard, a group of carpenters could be focused solely on manufacturing the ship's ribs, or frames. Because the proportions for a trireme's frames were established by rule of thumb, they could produce these curved wooden skeletons in batches, knowing that any frame from that batch would fit correctly into the hull of any trireme being built. Similarly, other teams could be pre-shaping the planks for the hull, or carving the standardized oar ports that would house the vessel's primary propulsion system. This was a revolutionary division of labor. It turned the chaotic shipyard into a hive of coordinated, simultaneous activity. The keel acted as the backbone, and once it was laid down by the master shipwright, the pre-fabricated frames could be mounted onto it at precise intervals. This established the ship's fundamental shape almost instantly. From there, the teams responsible for the hull planking could begin their work, attaching the pre-shaped planks to this ready-made skeleton. This method drastically reduced the time needed for the most complex part of the build. achieving the perfect hydrodynamic curve of the hull. The master shipwright's role shifted from meticulously overseeing every single cut to ensuring quality control, checking that the pre-made components were assembled correctly and that the overall structure remained true to the intended form. His expertise ensured that the modular parts came together into a cohesive and seaworthy whole. The efficiency gains from this system were enormous. It meant that a shipyard could be working on multiple ships at different stages of completion without descending into chaos. While one team was finishing the planking on a nearly complete hull, another could be starting the assembly of the frames on a new keel right beside it. This parallel workflow is what made feats like building 200 ships in 3 months even conceivable. They weren't building one ship at a time, they were building an entire fleet simultaneously, leveraging the power of standardized, interchangeable parts. This modular thinking extended beyond the ship itself to the very organization of the workforce, creating a production pipeline of stunning efficiency that allowed Rome to project naval power on a scale the ancient world had never seen before. The toolkit of the Roman shipwright was a study in elegant simplicity. There were no power saws, no hydraulic presses, no laser levels guiding their work. Instead, the shipyard would have echoed with the distinct sounds of fundamental hand tools. The rhythmic thunk of the adze biting into wood, the rasping pull of a large two-man saw, the sharp tap of a hammer driving a wrought iron nail, and the whirring spin of a bow drill. While this collection might seem rudimentary to our modern eyes, to dismiss it would be a profound mistake. The true genius was not in the complexity of the tools themselves, but in the absolute mastery with which they were employed. Each tool was an extension of the craftsman's skill, and together they were more than capable of shaping the ancient world's most advanced vehicles. Take the adze, for instance. This tool, which looks like an axe with a blade set at a right angle to the handle, was the shipwright's primary sculptor. It was with the adze that a rough-hewn timber was transformed into a perfectly curved hull plank, or a smoothly shaped frame. A skilled worker could use it with astonishing precision, shaving off thin ribbons of wood to achieve exactly the right thickness and curvature. He would work by feel and by eye, running a hand over the surface to check for any imperfections the blade had missed. This wasn't brute force, it was a delicate art. The adze allowed the shipwright to follow the natural grain of the wood, actually enhancing its strength rather than fighting against it, creating planks that were both lightweight and incredibly resilient. Precision joinery was achieved with another simple yet brilliant tool, the bow drill. This device consisted of a drill bit, a wooden spindle, and a bow whose string was wrapped around the spindle. By moving the bow back and forth, the carpenter could generate a rapid, controlled rotation. This allowed him to bore clean, exact holes for the wooden pegs, known as treenails, that locked the ship's structure together. The placement and angle of these holes were critical. If they were off by even a small margin, the planks wouldn't pull tight against the frames, compromising the hull's integrity. The bow drill, in the hands of an expert, provided the control necessary for this exacting work. It was a testament to their understanding that precision comes not from the tool's complexity, but from the skill of the person guiding it. The reliance on such simple implements placed the craftsman's expertise at the very center of the operation. Without complex machinery to guarantee uniformity, the quality of the ship was directly proportional to the knowledge in the worker's hands and the sharpness of his eye. A novice might hack away at a piece of oak with an adze, leaving a weak, uneven surface. A master, however, could read the wood like a map, understanding how its internal structure would respond to his tools. He knew exactly how to steam a plank to make it flexible enough to bend into the dramatic curve of the hull without snapping. He understood the correct angle to drive a trenail so that it would swell tight when soaked with seawater, creating a waterproof seal that would last for decades. This deep, tactile knowledge was what transformed a pile of raw materials into a seaworthy vessel. This intimate relationship between craftsman and material actually resulted in a hull that was uniquely suited to withstand the punishing environment of the Mediterranean. A ship built this way was not a rigid, brittle structure. It was designed to be flexible, to work with the sea rather than against it. As waves slammed into the hull, the carefully fitted planks and frames would shift minutely, absorbing the energy of the impact. The trenails, swelling with moisture, would keep the joints tight without being so rigid that they would crack under stress. A hull shaped by hand with an adze had a slight texture and variation that a machine-made surface lacks, which could actually help disperse the force of the water flowing past it. The Romans, through their simple tools and profound skill, were building organic structures that were perfectly adapted to their element, proving that technological sophistication is not always measured by gadgetry, but by a deep understanding of materials and forces. With the organizational genius of the modular system humming in the background, the moment of truth arrived, the physical birth of the ship. All the prefabricated parts, the teams of specialized workers, and the master shipwright's entire mental plan converged on one single foundational act: laying the keel. This was far more than just placing a long timber on the ground. It was a ceremonial and technical event of the highest importance. The keel was the spinal column of the entire vessel. Its length, determined by the type of ship being built, set the ultimate scale for everything that would follow. Its absolute straightness was non-negotiable, for any flaw here would be magnified exponentially as the ship grew upward and outward, resulting in a crooked, unseaworthy, and doomed creation. This was where the abstract knowledge in the shipwright's mind began its transformation into physical reality. But how do you translate a mental blueprint into a perfect, three-dimensional form without a single sheet of technical drawings? The Romans employed a brilliantly simple and scalable technique known as hole molding. Before a single piece of the keel was fastened, the shipyard floor itself became the drawing board. The master shipwright, perhaps with his most trusted apprentices, would clear a large, flat area of ground. Using a knotted rope for consistent measurement and a series of carefully placed wooden stakes, they would physically map out the entire shape of the ship's hull onto the earth. This wasn't a vague sketch. It was a full-scale outline, a giant diagram that every worker could see and understand. The positions of the keel, the sternpost, and most importantly, the critical frames were all marked with stakes. Guide ropes stretched between these stakes created the precise lines that would govern the entire construction. This ground drawing was the temporary, shared blueprint that aligned the entire team. It was within this outlined form that the shipwright's true artistry was displayed, as he established the two most critical curves that would define the ship's performance: the deadrise and the tumble home. These terms might sound technical, but their impact is easy to grasp. The deadrise refers to the angle at which the bottom of the hull rises from the keel. A flat-bottomed ship has very little deadrise. It's stable in calm water but pounds terribly in waves. A ship with a pronounced V-shaped hull has a lot of deadrise. It cuts through waves smoothly but can be less stable. The Roman shipwright used his experience to find the perfect balance for each vessel's purpose, carving the central frames to create a hull that was both seaworthy and stable. Then there was the tumble home, the inward curve of the hull above the waterline. If you look at a classic warship, the sides actually slope inward as they go upward. This wasn't just for aesthetics. It was a vital strategic feature. This inward slope made it exponentially more difficult for enemy boarding parties to scale the sides during battle. It also brought the topmost tier of oarsmen closer to the centerline, giving their oars more leverage and making the ship more maneuverable. Setting these curves correctly was an act of profound engineering intuition, blending hydrodynamics with military tactics. Once the keel was perfectly aligned, and the key frames were set according to the ground diagram, the skeletal structure of the ship began to emerge rapidly. The pre-fabricated frames, manufactured in batches based on the standardized rules, were now lifted into position and fastened to the keel. The master shipwright's role at this stage was one of supreme quality control. He would move along this growing wooden skeleton, using his experienced eye and a long, flexible baton to check the fairness of the lines. He was feeling for the sweep of the hull, ensuring that the curve from stem to stern was smooth and without any flat spots or sudden bulges that would create drag or weak points. This was the physical manifestation of his plan, a complex shape born from simple stakes in the ground and the unwritten rules in his mind, now standing as the robust foundation for a masterpiece of maritime engineering. With the keel firmly established as the ship's backbone, the shipyard transformed into a scene of controlled, creative chaos. This was the moment the vessel truly began to find its form, as the skeleton of ribs, or frames, rose around that central timber. But this wasn't a simple matter of grabbing identical, pre-cut pieces from a stack. Each frame had to be a unique component, custom fitted to its specific position along the hull to create the complex, flowing curves essential for seaworthiness. How could they possibly achieve such precision without a detailed plan to follow? The answer lies in a beautifully simple tool and a technique that turned the shipyard floor into a living, breathing design studio. The master shipwright and his crew employed a method known as lofting, using long, flexible wooden strips called battens. Imagine these battens as giant, bendable rulers. The shipwright would take one of these batten and, referring to the stakes and guide ropes of the ground drawing, would carefully bend it to match the intended curve of the hull at a specific point. He would then hold this perfect, sweeping curve in place, and a worker would quickly trace its shape directly onto the large, flat planking platform. This process was repeated for each major frame location, resulting in a series of full-size, arched outlines drawn right there on the work surface. These weren't abstract lines, they were one-to-one templates. A carpenter could now take a heavy, rough-cut timber, place it over the drawn curve, and skillfully chop and shape it with his adze until it was a perfect match. In this way, each frame was born directly from the master's vision, translated through the flexible batten into a physical component of breathtaking accuracy. This hands-on approach to geometry was incredibly sophisticated. It allowed the shipwrights to create what are known as compound curved surfaces that curve in multiple directions simultaneously, like the sleek hull of a modern sports car. A ship's hull doesn't just curve inward from bow to stern. It also curves upward from the keel to the waterline, and then tapers inward with the tumble home. Trying to define this shape with flat, two-dimensional drawings would have been immensely challenging. But by lofting the curves full size, the craftsmen could see and feel the exact shape they needed to build. They were working in 3 dimensions from the very start, solving complex geometric problems with a simple strip of wood and a trained eye. This practical method guaranteed that the ship would have what they called a fair hull, a smooth, uninterrupted surface without any flat spots or awkward bulges that would create drag or structural weak points. As each uniquely shaped frame was hoisted into position and fastened to the keel, the abstract forms sketched on the ground began to materialize as a 3-dimensional wooden skeleton. The shipwright would move constantly around this emerging structure, his hand running along the frames, his eyes scrutinizing the lines. He was checking for fairness in real time, ensuring that the transition from one frame to the next was seamless. If a frame was even slightly off, it would disrupt the entire flow of the hull, like a single wrong note in a musical scale. This meticulous, hands-on verification was the final, critical step in a process that blended artisanal skill with empirical engineering. The resulting framework was not a rigid cage, but a strong, organic form, perfectly shaped to slice through the water and withstand the ocean's power. All achieved through the timeless combination of human ingenuity and simple, effective tools. Now we come to the very heart of the mystery, the moment that separates Roman shipbuilding from almost everything that came after it. We are so accustomed to the modern way of building things, which is to start with the internal skeleton. Think of a house. You erect the frame first, the 2x4s that define the walls, and then you attach the outer shell, the siding, to that framework. For centuries, this skeleton-first approach has been the logical way to build a strong structure. But the Romans, in their brilliant defiance of convention, did the exact opposite. They built their ships from the outside in a method known to archaeologists as shell-first construction. It is a technique that seems almost backward, yet it resulted in a hull of legendary strength and flexibility. Here is how it worked. Instead of first building the complete wooden skeleton of frames and ribs, the Roman shipwrights began with the keel, and then immediately started attaching the planks of the hull directly to it, one by one, working upward from the bottom. They were essentially constructing the ship's skin before it had a skeleton. Picture it like building a wooden barrel. A cooper makes the staves first, binding them edge to edge with metal hoops to create a watertight container. The barrel's strength comes from the staves themselves pressing tightly together. The Romans were doing something very similar, but on the scale of a massive seagoing vessel. This required the shipwright to hold the entire, complex, three-dimensional shape of the finished hull perfectly in his mind's eye. There was no internal framework to guide him. The growing shell of planking was the guide. Each new plank had to be shaped with absolute precision to continue the smooth, fair curve of the hull, or the entire project would go awry. The key that made this seemingly precarious method not just possible, but phenomenally successful, was a joint so sophisticated it stands as a marvel of ancient engineering: the mortise-and-tenon joint. This was not a simple butt joint or a crude nail. For each plank, the craftsmen would carve a series of small, rectangular holes, or mortises, along the edge of the wood. On the opposing edge of the next plank, they would shape corresponding rectangular tabs, or tenons. When the two planks were brought together, these tenons would slot perfectly into the mortises, like a three-dimensional wooden puzzle. But the genius didn't stop there. Each tenon was then locked into place by driving a small wooden peg, called a trinale, through a hole drilled through both the plank and the tenon. This created an interlocking system that was incredibly strong, rigid, and most importantly, flexible. This method of joinery, known as edge-joined or carvel planking, transformed the hull into what modern engineers would call a monocoque structure. Think of an eggshell. An egg is incredibly fragile if you press on its ends, but it can withstand immense pressure from the sides. Its strength doesn't come from an internal skeleton. The curved shell itself is the source of its strength. A Roman ship-built shell first operated on the same principle. The mortise-and-tenon joints distributed stress evenly across the entire surface of the hull. When a wave slammed into the ship, the impact was absorbed and dissipated by the entire network of interlocked planks, which would flex minutely as a single unit. This created a hull that was both incredibly tough and surprisingly resilient, able to flex and work with the sea rather than fighting it as a more rigid, skeleton-first vessel might. The process of building this way was a slow, meticulous ballet of craftsmanship. Teams of workers would be carefully fitting each plank, drilling the holes, carving the tenons, and hammering in the pegs. The sound would have been a constant, rhythmic tapping, a testament to patience and precision. As the shell grew higher, temporary internal braces would be used to hold the shape, but the true structure was the planking itself. Only after the hull was largely complete would the internal frames be custom, fitted, and fastened inside the shell. This is the ultimate testament to the shipwright's skill. He wasn't following a pre-built frame. He was creating a perfect form out of thin air. And the frames were added later more for additional stiffness and to provide platforms for the decks and oarsmen than as the primary source of strength. The shell was the ship. This technique, demanding and time-consuming, produced vessels that were not just tools of empire, but masterpieces of organic engineering, perfectly harmonized with the unforgiving element they were built to conquer. So we have this brilliant shell-first construction method, but its entire success hinges on a single, deceptively simple component: the mortise-and-tenon joint. To truly grasp its importance, you have to forget modern nails and welding for a moment and think like an ancient carpenter. The fundamental challenge was how to join two long, curved planks of wood edge to edge in a way that would not only hold them firmly together, but also allow the entire hull to flex and move as a single, living entity on the sea. The Roman solution was a masterpiece of practical engineering, a locking system that was both incredibly strong and elegantly simple. Imagine holding two pieces of wood that you need to join. Along the edge of one, you carefully chisel out a series of small, rectangular slots. These are the mortises. On the edge of the other plank, you carve corresponding rectangular tabs that stick out. These are the tenons. It's like creating a three-dimensional wooden puzzle. When you bring the two planks together, the tenons slide perfectly into the mortises, creating a tight, seamless fit. But the real genius is the final step. A small hole is drilled through the face of the plank and directly through the tenon inside. A tapered wooden peg, a treenail, is then hammered into this hole, permanently locking the joint together from the inside out. This isn't just a connection. It's an interlocking system that transforms two separate pieces into one continuous surface. The sheer scale of this precision work is almost incomprehensible. A typical Roman merchant ship might be around 100 feet long. To build its hull, craftsmen would need to create tens of thousands of these individual joints, each one requiring hand carving to exacting tolerances. If a mortise was carved just a millimeter too wide, the joint would be weak. If a tenon was a hair too thick, it wouldn't fit, or it could split the plank when forced in. Every single one of these thousands of connections had to be perfect. This required an army of highly skilled carpenters, each one an expert with an adze, a chisel, and a bow drill, working with a level of consistency that rivals modern machine production. The sound in the shipyard wouldn't just be hammering. It would be the constant, meticulous tapping of wooden mallets and the whirring of drills, a symphony of precision. And the payoff for all this painstaking labor was a hull that behaved unlike any other. Unlike a ship held together primarily by rigid metal fastenings, a mortise-and-tenon hull was uniquely flexible. When a massive wave slammed against the side, the force didn't concentrate on a few weak points. Instead, it was distributed evenly across the vast network of interlocking joints. Each tenon acted as a tiny shock absorber, allowing the planks to shift minutely against each other, absorbing the ocean's energy. The entire hull could actually twist and flex along its length, working with the water rather than resisting it as a brittle, rigid structure would. This flexibility was a key reason Roman ships, could survive the brutal storms of the Mediterranean, where more inflexible designs would simply have been pounded to pieces. Perhaps the most remarkable property of this joint was its ability to create a self-sealing, watertight bond. The wooden treenails, or pegs, were made from a different type of wood than the hull planks, often a more porous variety like oak. Once the ship was launched, these pegs would absorb water and swell, pressing outward against the walls of the holes they were driven into. This swelling action created an incredibly tight, water-resistant seal that actually improved over time. A metal nail can rust and loosen, but a wooden peg in a mortise-and-tenon joint becomes tighter the more it is stressed by the sea. This ingenious use of the material's natural properties ensured that the hull remained tight and seaworthy for decades, a testament to a deep, almost intuitive understanding of the materials they worked with. This joint wasn't just a fastener. It was the very soul of the Roman ship, a tiny piece of engineering perfection repeated thousands of times over to create a vessel capable of conquering an ocean. Of course, a perfectly interlocked hull is only the beginning. All those meticulously crafted mortise-and-tenon joints created an incredibly strong structure, but wood, by its very nature, is porous. It swells and contracts, and on the vast, unforgiving sea, even the tiniest gap can lead to a catastrophic leak. Turning this magnificent wooden shell into a truly watertight vessel required a second layer of ingenious craftsmanship, a process focused on sealing the ship from the relentless ocean. This was the art of waterproofing, and the Romans approached it with the same systematic brilliance they applied to every other aspect of the build. The first line of defense was a material that has been used by sailors for millennia: pitch. The Romans would harvest resin from trees, particularly pines, and heat it to create a thick, sticky, black tar. This substance was then carefully brushed or poured into the seams between the planks while it was still hot and liquid. As it cooled, it would harden, creating a flexible, waterproof seal that could accommodate the natural movement of the hull. But they didn't stop there. To reinforce these pitched seams, they would often take a fibrous material, like tarred animal hair or strands of flax, and literally hammer it into the gaps before applying the final layer of pitch. This technique, known as caulking, served a crucial purpose. The fibers acted like a sponge, absorbing the liquid pitch and preventing it from simply dripping out while the ship was under construction. More importantly, they gave the sealant body and resilience, creating a gasket-like barrier that would remain effective even as the planks flexed and worked against each other in heavy seas. But the Romans, ever the practical engineers, knew that the sea presented more than just water. One of the most destructive forces a wooden ship could face was a hidden enemy, the teredo worm. This isn't a worm at all, but a peculiar saltwater clam with a long, soft body. The teredo worm is a master of destruction. It would burrow into the wooden hull, tunneling deep into the planks, and literally eating the ship from the inside out. A vessel infested with these creatures could have its structural integrity compromised in a frighteningly short time, leading to sudden and disastrous failure far from shore. The pitch and fiber caulking offered some protection, but the Romans developed a far more robust solution, one that we know about from the countless sheets of lead sheathing recovered from ancient shipwrecks. They would fashion thin, malleable sheets of lead and carefully nail them over the most vulnerable parts of the hull, particularly along the waterline and the critical seams between planks. These lead strips were fastened using small, hand-forged copper nails. The choice of materials was scientifically astute. Copper nails were used because they are highly resistant to corrosion in salt water, unlike iron nails which would have rusted away quickly, causing the protective sheathing to fall off. The lead itself created a physical barrier that was completely impervious to the teredo worm. The mollusk simply couldn't penetrate it. This multi-layered defense system, fibrous caulking soaked in pitch, topped with a durable lead armor, showcases a profound understanding of marine biology and material science. They weren't just plugging holes. They were engineering a long-term survival system for their vessels. This comprehensive approach to waterproofing meant that a Roman ship was built not just for a single voyage, but for a long career spanning decades. The combination of flexible, organic sealants and tough, inorganic armor allowed the hull to breathe and move without sacrificing its integrity. It was a testament to their holistic view of shipbuilding, where every component, from the massive keel to the smallest copper nail, had a deliberate and well-understood role to play. The ship wasn't merely constructed, it was meticulously prepared for a lifetime of battle against the elements, ensuring that the empire's vital arteries of trade and military power remained open, season after challenging season. With the hull sealed and ready for the sea, the shipyard's attention turned skyward, to the very element that would give the vessel its life, the wind. Installing the mast was not a simple matter of propping up a tall pole. It was one of the most critical engineering challenges of the entire build. The mast is the lever through which the immense and unpredictable power of the wind is transferred to the ship. In a fierce gale, the force trying to tear the mast from the hull is unimaginable. To handle this, the Romans engineered a component of brute strength and precision known as the mast step. This was not a small socket, but a colossal timber block, often hewn from a single enormous piece of heartwood oak. This block was strategically positioned over the keel, the strongest part of the ship, and then fastened to the framework with massive wooden trenails or even iron bolts. The mortise carved into its top was precisely shaped to cradle the base of the mast, or the mast foot, creating a firm interlocking joint. This entire assembly acted as the anchor, distributing the colossal stresses of sailing across the ship's entire backbone, ensuring that the mast remained standing even when the ship was being thrown about by a storm. The placement of this mast step was not a matter of guesswork. It was determined by the same proportional rules that governed the rest of the ship's design. The master shipwright knew that for a vessel of a given length and beam, the ideal position for the mast was a specific fraction of the way back from the bow. Getting this ratio correct was a matter of performance and survival. If the mast was placed too far forward, the ship would have a tendency to dig its bow into the waves, becoming difficult to steer and dangerously wet. If it was too far back, the stern would sit low, making the vessel sluggish and prone to being overtaken by following seas. The correct balance point allowed the ship to ride the waves gracefully, harnessing the wind's power efficiently. This is another stunning example of their rule-based design. The shipwright didn't need a complex calculation to find the sweet spot. He simply applied a time-tested ratio, a piece of knowledge refined through generations of successful voyages, and the ship was perfectly balanced as a result. Once the mighty mast was stepped into place, the intricate web of the rigging began to take shape. This was the nervous system of the ship, a complex network of hemp ropes that controlled the great square sail. The vocabulary of the rigging was extensive. The stays were the heavy ropes running fore and aft, preventing the mast from tipping over. The shrouds ran to the sides of the ship, providing lateral support. Then came the running rigging, the halyards to hoist the heavy sail up the mast, the braces to angle the yardarm to catch the wind, and the sheets to control the lower corners of the sail. Managing this web of lines required sophisticated hardware. The Romans used wooden blocks, which functioned as pulleys, to create mechanical advantage. A single sailor, by threading a rope through a block, could multiply his strength enough to hoist a sodden woolen sail that weighed as much as a small car. These blocks were marvels of craftsmanship in themselves, carved from tough, durable woods like elm, and fitted with polished sheaves to reduce friction. All of these ropes had to be anchored to something solid. Along the sides of the hull, strategically placed wooden cleats and robust timbers called knees provided the attachment points. The tension in these lines was phenomenal, and every component, from the hemp fibers to the wooden blocks to the hull itself, had to be engineered to withstand it. The entire system was a masterpiece of practical physics. The Romans understood the principles of leverage and tension intuitively. They knew how to arrange the ropes to give the crew maximum control over the sail with a minimum of effort, a crucial advantage during the chaos of a naval battle, or when trying to maneuver a heavy merchant ship into a crowded port. The sound of a Roman ship under sail would have been a symphony of controlled power. The hum of taut rigging, the creak of the mast in its step, and the snap of the great sail filling with wind, propelling a triumph of engineering across the ancient world. While the sail provided power for long journeys, the true soul of a Roman warship, its devastating speed and agility in battle, came from its oars. Designing the rowing system was arguably the most complex puzzle the naval architects had to solve. A breathtaking feat of ergonomic and structural engineering that went far beyond simply cutting holes in the side of the hull. Each warship was essentially a massive, floating machine, and the oarsmen were its living engine. The challenge was to house, organize, and synchronize dozens, and in the largest ships, hundreds of men, in a space that was cramped, dark, and perpetually in motion, all while ensuring their collective power could be transmitted efficiently to the water. The most famous of these systems was the multi-level arrangement, like the 3 tiers of a trireme or the 5 banks of a quinquereme. The very names of these ships were actually a numerical code describing their rowing configuration. A trireme didn't necessarily mean 3 perfectly stacked levels of oarsmen. A more likely arrangement was a staggered, seated formation where oarsmen on different levels were positioned in a sort of stepped diagonal, allowing each man the physical space to pull his oar. The term quinquereme is thought to refer not to 5 distinct tiers, which would have made the ship impossibly top-heavy, but to a system where multiple men, likely 5, were allocated to a single massive oar, or to a complex grouping of oars arranged in a multi-level pattern. This sophisticated arrangement was the result of centuries of evolution, a secret art perfected through relentless trial and error in the heat of naval combat. The core of the design problem was geometry, pure and simple. Imagine the inside of the hull, a cramped, curved space. Now picture oars of different lengths, emerging from oar ports located at different heights above the waterline, all needing to stroke in perfect unison. The oars from the upper levels had to be longer to reach the water, while those from the lower levels could be shorter. The critical task for the shipwright was to position the toles, the wooden pegs that acted as oarlocks, with absolute precision. Each tole had to be placed so that the arc described by the tip of every oar, from the catch in the water to the end of the stroke, was perfectly synchronized with the oar next to it, and, crucially, the oars above and below it. A miscalculation of just a few centimeters could be catastrophic, resulting in a tangled mess of clashing oars at the first stroke, rendering the ship a helpless target. This precise spacing was achieved not with complex mathematics, but through the shipwright's proportional rules and the use of full-scale templates. Before a single oar port was cut, the master shipwright would have determined the key measurement, the vertical distance between the rowing levels. This distance, likely derived from the ship's beam, dictated everything else. Using his flexible battens, he would map out the ideal sweep for each oar on the lofting floor. The position of the toll for each oar was the fixed pivot point. Its placement determined the leverage and the clearances. The oar ports themselves were not simple holes. They were carefully carved openings, often lined with leather to prevent splintering and to keep out water when the oar was shipped indoors. Their angle and shape were critical to allow the oar to move freely through its entire range of motion without binding. The knowledge of how to lay out this intricate, three-dimensional web of moving parts was among the most closely guarded secrets of the ancient world. A shipwright who possessed this knowledge could build a warship that could outmaneuver and outspeed any rival. It was a form of intellectual property more valuable than gold, passed down through apprenticeships. The result of this secret science was a machine of terrifying efficiency. When the hortator, the rowing master, beat his drum, the oars dipped and pulled as one. The power of 100 men or more was channeled through a perfectly calibrated system, allowing a massive quinquereme to accelerate with shocking speed, turn on a coin, or stop almost dead in the water. This wasn't just rowing. It was a symphony of coordinated human power, made possible by an engineering design so advanced that its principles remain impressive even today. All this intricate design and masterful craftsmanship had to happen somewhere. The creation of these maritime giants was not a cottage industry. It was a full-blown industrial enterprise, centered in vast, sprawling complexes known as shipyards, or navalia. If the master shipwright was the brain of the operation, the shipyard was its beating heart, a place where the chaotic energy of raw materials was transformed into the disciplined power of a Roman fleet. The scale of these operations was staggering, and to understand them is to grasp the true industrial might of ancient Rome. Major ports like Ostia, at the mouth of the Tiber River, Misenum near Naples, and Ravenna on the Adriatic coast, were not just harbors for ships. They were colossal factory towns dedicated entirely to naval construction and maintenance. Stepping into the Navalia at Ostia, for instance, would have been an overwhelming experience for the senses. The air would have been thick with the smells of fresh sawn wood, boiling pitch, and the acrid smoke of blacksmiths' forges. The soundscape was a constant, deafening symphony of industry. The rhythmic pounding of mallets, the screech of saws cutting through massive timbers, the shouts of foremen coordinating their teams, and the creak of ropes and pulleys moving heavy components into place. These were not simple open spaces with a few workbenches. They featured massive, roofed sheds that could protect multiple ships from the elements during construction. Most impressively, they often had stone-built slipways, inclined planes that led directly into the water. A newly built ship could be eased down these slipways in a controlled launch, a moment of high drama and celebration after months of labor. But the true genius of the Navalia was not just its physical infrastructure. It was its revolutionary organization of human skill. The division of labor within these yards was breathtakingly sophisticated. This wasn't a place where a single group of carpenters tried to do everything. Instead, it operated like a well-oiled machine, with each specialized team focusing on a single, repetitive task. A concept that would not be seen again on such a scale until the Industrial Revolution. There were the sawyers, teams of powerful men who operated massive two-man saws to rip enormous tree trunks into manageable planks and beams. The joiners were the true artists of wood, specializing in crafting the complex mortise-and-tenon joints with chisels and mallets, their work requiring a level of precision that bordered on the obsessive. In other parts of the yard, you would find the rope makers, or restiens, who worked in incredibly long buildings called rope walks, tirelessly twisting hemp or flax fibers into the miles of cordage needed for rigging. Nearby, the sail makers would be assembling vast sheets of heavy linen or wool. Stitching them together with incredibly strong seams to create the enormous square sails that could catch the Mediterranean wind. And everywhere the sound of hammer on metal would lead you to the blacksmiths, the fabbri, who were responsible for forging every metal component, from the massive, terrifying bronze ram that would be fitted to the prow of a warship, down to the thousands upon thousands of iron nails and delicate copper fastenings used in the lead sheathing. Each of these specialists was a master of their particular craft, and their ability to work in parallel, feeding their finished components to the central assembly teams, is what allowed for the incredible speed of Roman ship production. The shipwright was the conductor, but the orchestra was composed of these highly skilled sections, each playing their part in perfect harmony. Feeding this industrial machine required a supply chain of almost unimaginable scale and complexity. The demand for raw materials was insatiable. Just consider the timber alone. A single quinquereme could require the wood from an entire acre of ancient forest. The Romans had very specific requirements: tall, straight oaks for the keel and masts, flexible fir or pine for the hull planking, and tough elm for critical components like the mast step and the wooden blocks used in the rigging. This demand drove a massive logging industry. Forests in Italy were heavily exploited, but as the empire grew, the search for prime timber reached far afield, into the Balkans, Anatolia, and even the Lebanon, famous for its towering cedars. Getting these enormous logs from the forest to the shipyard was a logistical nightmare solved with typical Roman engineering brilliance. Logs would be dragged to the nearest river and floated downstream in massive rafts to the coast. There they would be loaded onto specially designed cargo ships, themselves products of the very shipyards they were supplying, and transported to the major navalia. This was not a seasonal operation. It was a constant flow, a vital artery keeping the heart of the empire pumping. But timber was just one part of the equation. The shipyards also needed tons of iron and copper ore to be mined, smelted, and forged into nails and tools. They needed flax and hemp to be grown, harvested, and processed into rope and sailcloth. They needed vast quantities of resin to be tapped from pine trees and boiled down into waterproofing pitch. Coordinating the arrival of all these disparate materials, ensuring that the sawyers never ran out of logs, the blacksmiths never ran out of iron, and the sailmakers never ran out of cloth, was a feat of administrative organization that rivals the military logistics of moving legions. The Roman shipyard was more than a place of construction. It was the epicenter of a vast economic web, a testament to an empire that understood that mastery of the sea began not with the launch of a ship, but with the controlled harvesting of a forest and the steady rhythm of a blacksmith's hammer. But for all the historical texts and logical deductions, there remains a gap between theory and reality. How can we be sure that this intricate system of shell, first construction and rule of thumb design actually worked as we imagine? The answer lies not in ancient libraries, but at the bottom of the sea. The true, unassailable evidence for Roman shipbuilding has been preserved for centuries in the cold, dark, oxygen-poor waters of the Mediterranean. Shipwrecks are more than just maritime tragedies. They are time capsules, offering us a direct, tangible connection to the shipwright's craft. Each wreck is a frozen moment in time, a ghostly blueprint of a vessel exactly as it was built, allowing archaeologists to reverse engineer the very thoughts of its creators. One of the most profound examples isn't even a Roman wreck, but it perfectly illustrates the technological lineage the Romans inherited and perfected. The Marsola Punic ship, discovered off the coast of Sicily, was a Carthaginian warship, a vessel of Rome's greatest rival, sunk around the time of the First Punic War. Its discovery was a revelation. When archaeologists meticulously excavated the hull, they found something astonishing. The names of the ship's parts were actually branded or painted onto the wood in Punic script. It was as if the ancient builders had left an assembly manual on the components themselves. More importantly, the wreck displayed the same shell first, mortise-and-tenon construction, that would become the hallmark of Roman naval architecture. This tells us that the Romans didn't invent this advanced technique out of thin air. They observed it, likely from captured enemy ships, recognized its superior strength, and then adopted and refined it on an industrial scale. It was a classic Roman strength, assimilating the best ideas of their adversaries and turning them into tools of their own domination. The wrecks of purely Roman vessels, particularly merchant ships, provide an even richer treasure trove of information. Unlike warships, which were often destroyed in battle or stripped of valuable metal, merchantmen frequently sank with their cargoes intact, settling gently into the seabed where silt and sand would preserve them for millennia. These wrecks are like open-air museums of maritime technology. Archaeologists can literally map the entire hull, plank by plank, joint by joint. They can see the precise spacing of the mortise-and-tenon fastenings, the exact angle of the cuts made by the shipwrights' adze, and even the tool marks left behind by individual craftsmen. This physical evidence confirms the use of prefabrication and modularity. By examining frames from the same wreck, researchers can determine if they were made from a standard template or individually fitted, providing concrete proof of the mass production techniques we discussed. Perhaps the most telling details found on these wrecks are the subtle signs of adaptation and repair. On several Roman merchant ships, archaeologists have discovered sections of hull planking that were clearly replaced after damage. These repair patches are not haphazard. They are expertly crafted inserts, fitted with the same mortise-and-tenon joints as the original hull, showing that repair crews in distant ports carried the same specialized knowledge as the original builders. Even more fascinating are the design modifications visible from one wreck to another. A ship built in the 2nd century might show a slightly different arrangement of frames than one from the 1st century, a tweak that likely resulted from accumulated experience. Perhaps the later design offered better stability in certain wind conditions, or was more resistant to a specific type of structural stress. These are not changes found in any manual. They are the physical record of incremental improvement, a process of trial and error written in wood and bronze. This evolutionary process is the final, crucial piece of the puzzle. Roman shipbuilding was not a static, monolithic tradition handed down unchanged for centuries. It was a living, breathing technology that evolved through brutal, real-world feedback. When a ship survived a terrible storm, its design was validated. But when a ship foundered, the lessons from that failure, whether a weak joint, a poorly balanced hull, or a mast step that shattered under pressure, would have been circulated among the guilds of shipwrights. The next ship built would incorporate that hard-won knowledge. The archaeological record shows this beautifully. Over time, the mortise-and-tenon joints in later wrecks are often spaced more closely together in areas of high stress, like the bow, indicating a learned response to the points where hulls were most likely to fail. The continuous refinement of the rowing systems, making them more efficient and less prone to jamming, would have been driven by the life or death demands of naval warfare. Every shipwreck, whether a victorious warship retired to the deep or a humble grain carrier lost to a sudden squall, contributed to a vast, collective database of engineering knowledge. It was a system that learned from disaster, ensuring that each new vessel launched was, in some small way, a better, safer, and more effective machine than the one that came before it. This remarkable process of learning from every shipwreck, whether friendly or hostile, points to a broader truth about Roman technological prowess. they were masterful adapters. Their shipbuilding genius did not emerge fully formed from Italian shipyards. It was sparked by a moment of profound necessity and a willingness to learn from their enemies. The single most pivotal event in the entire history of Roman naval development was not a peaceful innovation, but a desperate act of wartime reverse engineering. Early in the First Punic War, the Romans faced a terrifying reality. They were a land power, masters of the legion, but they were being systematically outmaneuvered at sea by the Carthaginians, the supreme naval power of the Western Mediterranean. The Carthaginian quinquereme was the ultimate weapon of its day, a colossal, fast, and highly maneuverable warship that Roman vessels simply could not match. After a series of disastrous engagements, it became brutally clear that to survive, Rome had to build a navy, and it had to do so overnight. The legend, passed down by historians like Polybius, tells of an almost miraculous opportunity. A Carthaginian quinquereme, perhaps damaged in a storm, ran aground on the coast of Italy. This wasn't just any wreck, it was an intact, state-of-the-art vessel, a treasure trove of classified enemy technology that had literally washed up on their doorstep. The Romans didn't see a piece of debris, they saw a blueprint. They immediately seized the ship and ordered their best engineers, their most skilled woodworkers, and their sharpest military minds to take it apart, piece by piece, joint by joint. This was not a casual inspection. It was a systematic, forensic deconstruction. They catalogued every component, from the massive keel to the smallest trenail. They measured the angle of the hull's curve, the precise spacing of the oar ports, the sophisticated arrangement of the mast step. They were not just looking at what the ship was, but how it was built, deciphering the construction sequence and the design principles that made it so effective. This act of technological espionage bypassed the entire need for formal blueprints or written manuals. The knowledge they gained was not theoretical. It was tactile, three-dimensional, and immediately applicable. The Carthaginian ship itself became the ultimate instruction manual. By studying this captured vessel, the Roman shipwrights absorbed centuries of accumulated Phoenician and Carthaginian maritime expertise in a matter of weeks. They learned the secrets of the shell-first construction method and the mortise-and-tenon joinery that gave the hull its legendary strength and flexibility. They understood the complex geometry required to house multiple banks of oarsmen effectively. Most importantly, they grasped the overall proportions and ratios that determined a quinquereme's seaworthiness and combat performance. This wasn't about copying a single ship. It was about internalizing an entire system of shipbuilding. Armed with this stolen knowledge, Rome embarked on one of the most ambitious industrial projects of the ancient world. They didn't just build one or two test ships. According to the historical accounts, they used the captured vessel as a template to construct an entire fleet of 100 quinqueremes and 20 triremes in an astonishingly short 60 days. To achieve this, they couldn't rely on a single, slow, custom-built process. The very act of mass-producing these complex warships so quickly forced them to innovate the modular prefabrication system we discussed earlier. They broke down the Carthaginian design into its component parts and established standardized procedures for manufacturing each one. The captured ship provided the master template. Roman industrial organization provided the means to replicate it on a massive scale. The result was a fleet that could suddenly stand toe-to-toe with the masters of the sea. But the Romans didn't stop at mere imitation. True to their form, they absorbed the Carthaginian technology and then improved upon it with a characteristically Roman innovation, the corvus, or the raven. This was a boarding bridge that could be swung down onto an enemy ship's deck, effectively turning a naval battle into a land battle, a fight where the Roman legionary was invincible. This addition demonstrates that their reverse engineering was a starting point, not an end goal. They adopted the superior hull design of their enemy, but then modified it to suit their own unique military strengths. The story of the captured quinquereme is therefore a perfect metaphor for the entire Roman Empire. It reveals a culture that was pragmatic, fiercely ambitious, and brilliantly adaptive, capable of recognizing superior technology, learning its secrets through direct physical examination, and then scaling it up with ruthless efficiency to serve their own world-altering ambitions. This glaring absence of written manuals brings us to a fascinating figure and a crucial piece of evidence: the Roman engineer and architect Vitruvius. In the 1st century BC, Vitruvius penned De Architectura, a sprawling multi-volume work that stands as the most complete treatise on engineering and architecture to survive from the ancient world. It's a breathtakingly comprehensive document, covering everything from city planning and the construction of temples to the sourcing of water and the properties of building materials. For anyone hoping to find the lost blueprints for a Roman warship, Vitruvius's work seems like the most promising place to look. But when we turn the pages, searching for the secrets of the naval architects, we are met with a profound and telling silence. Vitruvius does mention ships, but his treatment is surprisingly superficial, especially when compared to the minute detail he provides for other structures. He briefly discusses the different types of vessels, acknowledging the existence of triremes, quinqueremes, and merchant ships. He even touches upon the all-important concept of proportions, noting that a ship's length-to-beam ratio is critical for its performance. But here the detail stops. He provides no step-by-step instructions, no diagrams for laying out a hull, no explanation of the mortise-and-tenon technique, and no insight into the complex ergonomics of the rowing system. For the man who explained how to build a perfect basilica, or how to calculate the precise pitch of an aqueduct, this omission is not an accident. It is a powerful clue. This selective coverage reveals a critical distinction in the Roman mind between different fields of technical knowledge. Vitruvius was writing about architecture, the art of building permanent, stable structures on solid ground. His principles were based on symmetry, geometry, and stability. Shipbuilding, however, belonged to a different category altogether. A ship was not a static object. It was a dynamic machine designed to survive in a fluid, hostile, and constantly moving environment. Its engineering principles were not just about stability, but about flexibility, hydrodynamics, and managing immense, shifting forces. Vitruvius's work shows us that this knowledge was considered a specialized craft, an ars separate from the architect's domain. It was the realm of the navalis architectus, the shipwright, whose expertise was rooted in practice and tradition, not in the theoretical geometries of the educated elite. The very way Vitruvius writes about ships reinforces this idea. When he describes a temple, he provides exact mathematical ratios for every part. But when he describes a ship, he speaks in generalities, almost as if he is an observer summarizing what he has seen rather than an expert explaining what he has done. This suggests that the deep, tacit knowledge of ship construction, the feel of the adze, the rules for lofting the hull curves, the secrets of the rigging, was not something that was widely written down because it was not considered appropriate for his literary project. That knowledge lived elsewhere, in the shipyards, in the hands of the craftsmen, and in the oral traditions of their guilds. Vitruvius's silence is, paradoxically, one of the loudest testaments to the existence of this separate, vibrant, and highly advanced world of practical engineering. What Vitruvius does choose to include is equally revealing. His mention of proportions aligns perfectly with the rule of thumb system we discussed earlier. He confirms that the fundamental principles of naval architecture, were based on harmonious ratios, a concept that would have been very familiar to any Roman engineer. This was the common language, the bridge between the theoretical world of the architect and the practical world of the shipwright. Both understood that good design was based on proportional relationships. But while the architect could draw these ratios on parchment, the shipwright had to translate them into a three-dimensional, seaworthy structure using battens and stakes on a shipyard floor. Vitruvius gives us the what, the importance of proportions, but his work pointedly omits the how, leaving that crucial, practical knowledge exactly where it belonged, in the custody of the master craftsmen who had spent a lifetime mastering it. But of course, the true measure of any weapon is not how it looks in the shipyard, but how it performs in the chaos of combat. All the sophisticated joinery, the harmonious proportions, and the modular efficiency would mean nothing if these ships failed when put to the ultimate test. And for the Romans, that test came early and often. Against the greatest naval power of the age, Carthage, the Battle of Mylae in 260 BC was their first great naval victory, and it serves as a perfect case study for how their unique approach to shipbuilding translated directly into battlefield dominance. The Romans, remember, were novice sailors facing the descendants of the Phoenicians, masters of the Mediterranean for centuries. A conventional naval battle, relying on the complex art of ramming and maneuvering, would have been a certain disaster. The Carthaginians were experts at steering their agile quinquiremes to smash into the sides of enemy vessels, shearing off oars and punching holes in hulls. But the Romans had a secret weapon, one that was as much a product of their engineering mindset as the ships themselves, the corvus or raven. This was a massive boarding bridge pivoted on the deck of the Roman ship. At its business end was a heavy, pointed spike of iron. When a Roman vessel closed with an enemy, this bridge would be swung around and dropped onto the opposing deck, the spike slamming down to grip the planking, creating an instant, stable pathway. What followed was not a sea battle. It was an infantry assault on the water. Roman legionaries, the most formidable soldiers in the world, would charge across the bridge and turn the enemy's ship into a bloody killing ground. The success of the corvus tells us something crucial about the ships that carried it. This device was not light. It added significant weight high up on the vessel, which in any lesser ship would have created a dangerous top heaviness, making it unstable and prone to capsizing, especially in the swell of the open sea. The fact that Roman quinquiremes could not only carry the corvus, but remain stable enough to deploy it effectively, is a powerful testament to the inherent stability designed into their hulls. The master shipwrights, using their rules of thumb for beam and balance, had unconsciously created a platform robust enough to support this radical new weapon. The ship's strength was not just in its ability to withstand a ramming attack, but in its capacity to serve as a stable base for a fundamentally new kind of warfare. At Mylae, the Carthaginian fleet, confident in its superior seamanship, was utterly confounded. Their tactical playbook was rendered useless as one ship after another was captured by Roman boarding parties. The battle was a stunning victory, proving that Roman naval architecture was not about outsailing the enemy, but about outthinking them, turning a naval engagement into a contest where their land-based strengths were decisive. Beyond specific gadgets like the corvus, the general resilience of Roman warships became legendary. We often picture ancient naval battles as quick, violent affairs ending in a single ramming strike. While ramming was a key tactic, it was rarely an instant kill. More often, it was a crippling blow, intended to disable an enemy's oars and rudders, leaving it dead in the water and vulnerable to boarding. For the targeted ship, survival depended on its ability to absorb that initial, catastrophic impact without breaking apart, This is where the shell first, mortise-and-tenon construction truly proved its worth. Remember, this method created a monocoque hull, a single flexible unit. When a bronze ram struck, the force was distributed across the entire network of interlocking planks. The hull would give and flex, dissipating the energy of the blow. A more rigid, skeleton-first hull might have simply shattered on impact. Roman ships were famously tough to sink, often remaining afloat and fightable, even after taking significant damage. This resilience gave their crews a crucial psychological edge. They knew their vessel was a survivable platform, which in turn fostered the aggressive, close-quarters tactics that became their trademark. This durability was tested not just by enemy arms, but by the sea itself. The Mediterranean, for all its postcard beauty, can transform in an instant into a cauldron of violent storms. Fleets were often lost not to enemy action, but to sudden squalls. The ability of a ship to weather a storm was a direct function of its construction. The flexible, shell-first hull was perfectly suited for this. As massive waves tossed the ship about, the hull could work with the water, twisting and bending to accommodate the stresses. The tightly fitted planks, sealed with pitch and reinforced with lead, kept the sea where it belonged on the outside. This seaworthiness allowed the Roman navy to operate across longer seasons, and in more challenging conditions than many of their rivals, extending their reach and ensuring that their logistical supply lines, the vital arteries of the empire, remained open. A merchant ship built with the same techniques could reliably carry grain from Egypt or wine from Spain. Its survival probability calculated not in blueprints, but in the proven performance of thousands of voyages before it. The ultimate demonstration of this naval supremacy came centuries later, at the Battle of Actium in 31 BC. This was the climactic clash between the fleets of Octavian, the future Emperor Augustus, and the combined forces of Mark Antony and Cleopatra. It was a battle of staggering scale, involving hundreds of ships on each side. Antony and Cleopatra's fleet included massive, tens and larger vessels, towering fortresses on the sea. Octavian's fleet, commanded by the brilliant Admiral Agrippa, relied on smaller, more agile Liburnians, a type of swift bireme perfected through years of warfare. The battle was a masterclass in the evolved Roman way of war at sea. Agrippa's ships, benefiting from their nimble design and the hardened, experienced crews, avoided direct confrontations with the heavier enemy vessels. Instead, they used their speed and maneuverability to outflank, harass, and isolate their opponents, using catapults and incendiary missiles to weaken them before moving in for the kill. The larger ships of Antony's fleet, sluggish and difficult to command in the confused fighting, were systematically overwhelmed. Actium was not won by a single technological trick like the Corvus, but by the complete integration of superior ship design, expert seamanship, and tactical genius. It showed a navy that had fully matured. Its shipbuilding principles, refined over 3 centuries of constant warfare, into an instrument of unparalleled effectiveness. This long, unbroken record of naval dominance, spanning from the rise against Carthage to the consolidation of the empire at Actium, is the most compelling argument for the Roman methods. You cannot fake success on that scale for that long. The empirical rule-of-thumb approach, passed down through apprenticeships and refined through the brutal feedback of battle and shipwreck, produced vessels that were perfectly adapted to their purpose. They were not the most elegant ships, nor were they necessarily the fastest under sail alone, but they were arguably the most robust, versatile, and strategically effective warships the ancient world ever produced. Their design was not frozen in a static blueprint. It was a living tradition, evolving with every lesson learned from a storm-tossed voyage or a hard-fought engagement. The proof of their genius is written not on parchment, but in the historical record of centuries of maritime supremacy, a dominance built by ships that were, in every sense of the word, conceived and born without a map. To truly grasp the sheer brilliance of the Roman system, we need to step outside of the ancient world and look at what came after. Following the collapse of the Roman Empire in the West, the vast, organized shipyards of the Mediterranean fell silent. The intricate knowledge of the Navales architectus, the proportional rules, the shell-first method, the mastery of the mortise-and-tenon joint, did not vanish overnight, but it did fragment and recede. For centuries, the art of building large seagoing vessels entered a different phase, one that highlights just how unique the Roman approach had been. By comparing it to the shipbuilding traditions of the medieval and Renaissance eras, the Roman achievement shines even brighter, revealing a technological peak that would not be matched in certain key aspects for over a millennium. In the centuries after Rome's fall, a different technique began to dominate European shipbuilding, particularly in the stormy North Sea and the Atlantic: skeleton-first construction. Imagine the complete opposite of the Roman method. Instead of building the waterproof shell first and then adding the internal framing, medieval shipwrights would start by erecting a complete internal skeleton: the keel, the stem and sternpost, and all the ribs or frame. Only after this wooden skeleton was standing would they nail the hull planking onto it. This was a fundamentally different philosophy. The strength of the vessel now resided primarily in its internal framework, with the outer planks acting more like a skin stretched over a rigid cage. This technique, known as clinker construction, where the planks overlap each other like clapboards siding on a house, was effective for the smaller, robust vessels needed for coastal trade and Viking exploration. It was a pragmatic adaptation to different materials, like the abundant softwoods of Northern Europe, and different maritime challenges. However, it lacked the monolithic, flexible strength of the Roman shell. A clinker-built hull was more rigid, and could be prone to leaking along the overlapping seams if the caulking failed, as the entire structure depended on the fastenings holding the planks to the frames. This shift from shell first to skeleton first was not necessarily a step backward in a linear sense, but rather a divergence driven by different needs and a broken chain of knowledge. The large-scale, standardized production of massive warships and granaries was no longer a priority for the fragmented kingdoms of the early Middle Ages. Shipbuilding became a more localized craft, with styles varying greatly from region to region. The complex logistics of sourcing the specific hardwoods and the armies of specialized craftsmen needed for Roman-style construction became impossible to sustain. The deep empirical understanding of hydrodynamics necessary to design a hull by eye, using battens and proportional rules, gave way to more rule-of-thumb methods that were passed down within small, isolated communities. The result was that the consistent, empire-wide standard of shipbuilding excellence set by Rome was lost. A ship built in England might share little with one built in Italy, beyond the basic principles of floating. The real turning point, and the moment that underscores the Romans' intuitive genius, came during the Renaissance. As Europe emerged from the Middle Ages, its horizons expanded dramatically. The age of exploration demanded ships capable of vast ocean voyages, vessels larger and more complex than anything built since the days of the Roman corbitta. To meet this challenge, shipwrights could no longer rely solely on tradition and rule of thumb. They began to create something the Romans seemingly never needed: detailed architectural drawings and intricate, scaled-down models. These were the true blueprints, the two-dimensional plans that guided the construction of three-dimensional giants. The adoption of these tools represents a fundamental shift from an empirical, tactile knowledge to a theoretical, mathematical one. Renaissance engineers were now designing their ships on paper first, calculating curves and displacements with geometry, before a single tree was felled. This was a monumental advancement, but it also serves as a telling contrast. The fact that Renaissance shipwrights felt the need to develop detailed plans suggests that the kind of intuitive, shared mental template used by the Romans had been lost. The complex, compound curves of a caravel or a galleon were too difficult to communicate and execute reliably using only verbal instructions and simple proportional rules. The blueprint was a solution to a problem that Roman organization and apprenticeship had seemingly solved without one. In a way, the Renaissance reliance on drawings acknowledges a gap in the continuity of craft. They were reinventing, through science and drafting, a systematic approach to shipbuilding that Rome had maintained as a living, oral tradition. The Roman method was so deeply ingrained in their industrial culture that it functioned with efficiency that later civilizations, with all their technical drawing skills, would spend centuries striving to replicate in terms of speed and scale. When we place these three eras side by side, the distinctiveness of the Roman achievement becomes stunningly clear. The medieval period represents a successful but different technological path, adapted to a changed world. The Renaissance marks a brilliant new beginning, fueled by scientific inquiry and global ambition. But the Roman system stands apart as a unique fusion of artisanal skill and industrial organization. They built some of the most sophisticated and durable ships of the ancient world, using a method that required no detailed plans, yet achieved a level of consistency and scale that would not be seen again until the dawn of the modern era. Their shell-first, mortise-and-tenon technique produced hulls with a legendary toughness that later skeleton-first methods often lacked. The ability to launch a fleet of hundreds of virtually identical warships in a matter of months was a logistical feat that medieval kingdoms could not have dreamed of, and one that would have impressed even a Renaissance admiral. This comparison doesn't diminish the accomplishments of later shipwrights. Rather, it elevates the Romans. It shows that their mastery was not just about building ships, but about perfecting a system of knowledge, a system of production, and a system of empire that allowed them to dominate the Mediterranean for centuries, all conceived and executed without a single surviving blueprint. This rigorous system of practical knowledge could not be confined to a single brilliant mind. It had to be replicated across generations and throughout the vast expanse of the empire. The true repository for the secrets of Roman shipbuilding was not a library, but the living, breathing memory of the craftsmen themselves. The entire enterprise hinged on an unbroken chain of teaching and learning, a deeply immersive process of apprenticeship that began not in a classroom, but in the sawdust-filled air of the shipyard. A young boy, perhaps the son or nephew of a shipwright, would enter this world at a remarkably early age, his education commencing with the most humble of tasks. His first lessons were not about lofty principles of design, but about the fundamental character of the materials. He might be tasked with sorting nails by size, or with preparing the caulking materials, his small hands learning the sticky, tactile feel of tar and oakum. This was not busywork. It was the first step in building an intuitive, physical understanding of the craft. His progression was gradual and meticulously supervised by the master. As he grew older and stronger, he would graduate to more complex duties, perhaps serving as a holder-on for a two-man saw, feeling the immense strain and rhythm of converting a massive log into planks. He would spend countless hours simply observing, watching the master shipwright pace the ground drawing, his eyes tracing the curves laid out by the battens. The lessons were almost never delivered as formal lectures. Instead, knowledge was passed down through demonstration and correction. The master might shape a tenon with a few expert strikes of his adze, then hand the tool to the apprentice and gesture for him to try. The learning was in the doing, and in the master's critical eye that caught every misplaced blow, every deviation from the perfect line. The apprentice learned to judge the quality of a joint by the sound the mallet made when driving the treenail home. A solid thunk meant success. A hollow sound signaled a flaw. This method ensured that the most valuable knowledge, the mysteries of the craft, remained securely within a closed circle. These were not sinister secrets, but rather the accumulated, proprietary wisdom that gave a particular shipwright or a family-led workshop its competitive edge. The precise ratios used for a specific type of vessel, the subtle tricks for steaming a particularly stubborn piece of timber, the preferred source for the most resilient oak, these were pieces of information as valuable as any trade secret in a modern corporation. This knowledge formed the intellectual capital of what we might think of as guild-like associations, though the Romans did not have formal guilds in the medieval sense. These WERE Chinese letter knit groups, bound by blood, patronage, or a shared oath to protect their collective expertise. This system of guarded knowledge guaranteed a remarkably high standard of quality control. Since a master's reputation was tied directly to the seaworthiness of his ships, he had a vested interest in ensuring his apprentices attained true mastery before they ever worked independently. The ultimate goal was to internalize the craft so completely that it became second nature. A master shipwright did not need to consciously recall the rule that the mast step should be placed 2/5 of the way back from the bow. His hands and eyes simply knew where it belonged. He could feel the fairness of a hull curve by running his palm along the planking, detecting imperfections invisible to an untrained eye. This embodied knowledge, stored in muscle memory and refined intuition, was what allowed for the incredible speed and consistency of Roman shipbuilding. It meant that in shipyards from Hispania to Syria, different crews of men, who had never met, could all build a trireme that performed identically. They were all applying the same deeply ingrained mental template, a shared understanding of Romanness in ship design that was communicated not through documents, but through the skilled hands of countless masters and apprentices across centuries. This living library of technique, passed from one generation to the next through watchful eyes and practiced hands, was the ultimate, unbreakable blueprint that enabled an empire to rule the waves. Yet for all our historical texts and underwater archaeology, there remains a question that can only be answered by getting our hands dirty, by feeling the weight of the adze and the strain of the ropes ourselves. This is the realm of experimental archaeology, a field dedicated to testing historical theories, not in libraries, but through the tangible, often grueling, process of reconstruction. It's one thing to admire the elegant lines of a shipwreck on a diagram. It's another to attempt to build a seaworthy vessel using only the tools and techniques available 2,000 years ago. These modern projects are the ultimate test of our theories about Roman shipbuilding, bridging the gap between scholarly hypothesis and physical reality. One of the most ambitious and illuminating projects in this field wasn't a Roman ship at all, but its close relative, the Greek trireme. The Olympias project, launched in the 1980s, set out to answer many of the same questions we have about Roman naval power by building a full-scale, functioning trireme. The challenges began immediately. The team of historians, naval architects, and skilled woodworkers had to interpret ancient descriptions and vase paintings, turning two-dimensional art into a three-dimensional, ocean-going machine. The construction process itself was a revelation. They discovered that building the hull shell first with mortise-and-tenon joints was incredibly labor-intensive, requiring thousands of hours of precise handwork. But the payoff was a hull of remarkable strength and flexibility, exactly as the archaeological evidence suggested. The real test, however, came when the Olympias was launched. Rowing the vessel with a full crew of volunteers provided breathtaking insights. They learned that a trireme was capable of astonishing bursts of speed and agility, but that coordinating 170 oarsmen required immense skill and physical endurance from everyone on board. The project proved that the ancient descriptions of naval warfare were not exaggerations. These ships were terrifyingly effective weapons systems, and their construction methods were perfectly suited to their deadly purpose. While a full-scale Roman warship like a quinquereme has yet to be rebuilt, a project of staggering cost and complexity, smaller replicas of Roman merchant ships have been attempted, offering a more intimate view of the civilian side of their maritime world. These projects, often undertaken by dedicated teams of archaeologists and volunteers, face the same practical problems a Roman shipwright would have faced. Sourcing the correct timber is a major hurdle. Finding large, curved oak pieces for the frames isn't a matter of going to a lumber yard. It requires locating specific trees with the right natural shape, just as the Romans did. The process of shaping the planks with hand tools is slow and physically demanding, teaching the builders to appreciate the sheer muscle and skill embedded in every ancient hull. Perhaps the most profound moment in any such project is the launch. After years of work, seeing a vessel built with ancient methods slide into the water and actually float is a powerful validation of the archaeological theories. But it's also a moment of truth. Does the hull leak? How does it handle in a light breeze? Does it feel stable? The behavior of these replica ships provides a direct, unmediated feedback loop that no amount of study can replicate. These reconstructions consistently highlight the immense intuitive skill of the ancient craftsmen. A modern carpenter, no matter how skilled, is initially at a disadvantage. We are trained in a world of power tools and perfect measurements. The Roman shipwright worked by eye and by feel. Modern builders of replicas often speak of a learning curve, a period where they have to unlearn modern precision and develop a new kind of judgment. They learn to read the wood, to understand how a plank will bend when steamed, and to trust the proportional rules that initially seem imprecise. Through this struggle, they gain a deep, empathetic understanding of the Roman mindset. They come to realize that the lack of blueprints wasn't a limitation. It was a reflection of a different kind of knowledge, one that was embodied and practical rather than theoretical. The ancient shipwright didn't need a drawing because he could see the finished ship in the grain of the timber and feel its curves in the swing of his adze. These experimental voyages also bring to light the challenges the Romans overcame as a matter of routine. A replica ship might reveal, for instance, that a certain joint is particularly vulnerable to stress in heavy seas, or that the placement of a specific frame creates an unexpected harmonic vibration when the ship is under oar. These are not failures of the ancient design, rather they are clues. They suggest that the Romans, through long experience, had already identified these potential failure points and had developed subtle modifications to address them. Modifications we can sometimes detect in the archaeological record of later shipwrecks. Every problem encountered by a modern crew sailing a replica is a window into a problem that an ancient captain and his shipwright had to solve. It transforms our understanding from a static appreciation of a museum piece into a dynamic recognition of a living, evolving technology that was constantly being refined through real-world use. By literally getting our hands on the ropes, we don't just learn how they built their ships. We begin to understand how they thought, how they solved problems, and how they mastered the sea not with abstract science, but with practiced, brilliant craftsmanship. Yet the legacy of Roman naval engineering did not simply sink beneath the waves with the empire itself. While the political structure of Rome crumbled, the profound technological and organizational principles they had perfected lingered, absorbed into the maritime traditions of the Mediterranean and influencing shipbuilding for centuries to come. Their methods became a kind of submerged foundation, upon which later powers would unconsciously build. The most direct and stunning continuation of this legacy is found not in the following century, but nearly 1,000 years later, in the rise of another maritime republic, Venice. The Venetian arsenal, established in the early 12th century, stands as a spiritual and functional successor to the great Roman Navalia. At its peak, this enclosed complex was the most concentrated and efficient shipbuilding center the world had seen since the days of Ostia and Misenum. While Venetian shipwrights used different construction techniques, having adopted the skeleton first, frame-based method that became standard in the medieval period, they perfected the Roman concept of the industrialized, state-controlled shipyard to an astonishing degree. The arsenal was a city within a city, a massive walled facility where every component of a ship, from pre-shaped timbers to pre-rolled sails, was produced in a continuous flow. The famous account of Henry Roman III of France, visiting in 1574, captures this perfectly. As he was led through the arsenal, a fully equipped galley was launched before his eyes in the time it took for his banquet to be served. This feat of speed was not achieved through magic, but through the same principles of standardization, prefabrication, and a highly specialized division of labor that the Romans had pioneered. The Venetians had rediscovered, independently or through a faint cultural memory, the immense power of organizing shipbuilding as a linear, synchronized industrial process. Beyond the sheer scale of production, the Roman emphasis on durability and strategic design also cast a long shadow. The shell-first, mortise-and-tenon technique may have faded from common use in the early Middle Ages, but the underlying goal of building robust, seaworthy vessels remained. Later Mediterranean powers, from the Byzantines with their formidable dromons to the navies of the Italian city-states, inherited the Roman understanding that naval supremacy was as much a function of logistics and resilient ship design as it was of tactical brilliance. The Roman approach to solving naval challenges through engineering innovations, like the corvus, established a precedent. It demonstrated that a naval power could compensate for a lack of traditional seafaring experience by leveraging its strengths in organization and technological adaptation. This lesson was not lost on later empires. The ability to rapidly build and maintain a large fleet, a capability the Romans demonstrated time and again during the Punic Wars, became the gold standard for any state with territorial ambitions. The very idea that a nation could transform itself from a land power into a dominant sea power through sheer industrial will is a fundamentally Roman concept, one that would be repeated by other rising powers throughout history. Perhaps the most enduring legacy, however, is not found in a specific joint or a shipyard layout, but in the conceptual framework the Romans applied to the sea. They were among the first to treat the Mediterranean not as a barrier, but as a unified, manageable space, a mare nostrum, or our sea. This required a systematic approach to maritime infrastructure that went far beyond the warships themselves. They established and maintained a network of protected harbors, lighthouses like the famed Pharos of Alexandria which they maintained, and navigational aids. They developed sophisticated legal and commercial systems for maritime trade, ensuring the smooth flow of goods that was vital to the empire's stability. In this way, Roman naval ingenuity was about more than just shipbuilding. It was about creating an integrated system of control, commerce, and communication. This holistic view of sea power, where the ship, the port, the law, and the trade route are all part of a single interconnected system, is their greatest gift to subsequent maritime history. It is a mindset that allowed an empire to cohere across vast distances, and it is a model that every great naval power since, whether consciously or not, has had to confront and in some way emulate. The echoes of Roman thought can be perceived in the global trade networks of the British Empire, and even in the strategic doctrines of modern superpowers, proving that the true blueprint they left behind was not for a ship, but for an entire way of mastering the world through the mastery of the sea. Even with the incredible insights gained from shipwrecks and experimental reconstructions, the world of the Roman shipwright still holds on to some of its most profound secrets. We have pieced together the broad strokes of their methods, but the finer details of their technical artistry, the subtle calculations and the unwritten nuances of their craft continue to elude us, pushing the boundaries of modern research. One of the most tantalizing gaps in our understanding lies in the realm of hydrostatics. How did they predict with such confidence how a new ship would sit in the water? Today, naval architects use complex mathematical models to calculate a vessel's displacement, its center of gravity, and its center of buoyancy, all critical factors that determine whether a ship will be stable and seaworthy or capsize on its maiden voyage. The Romans clearly possessed this knowledge, as their ships were consistently well balanced, but they left behind no formulas, no treatises on fluid dynamics. The most compelling theory is that their understanding was entirely empirical, built up over generations of observation. A master shipwright would have known that a hull with a certain set of proportions, a specific curvature to its belly, would displace a predictable amount of water. He might have used simple physical tests, perhaps loading scale models in a tank to observe their behavior, but the exact mental process he used to translate a lifetime of watching ships float into a perfect first draft for a new design remains one of the great unrecorded feats of ancient engineering. The techniques of lofting, of transferring the full-scale curves of the hull from the master's mind to the shipyard floor, are another area of active investigation. We understand the basic principle of using stakes and flexible battens, but the specific geometric rules they followed to ensure every curve was fair are still not fully decoded. Was it a system based on arcs of circles, or did they use more complex parabolic curves? Some researchers are now applying advanced digital modeling to the precise measurements taken from well-preserved wrecks, searching for recurring mathematical patterns in the hull line. The hope is to reverse engineer the secret recipe, the exact series of proportional relationships that would allow a shipwright, with just a few key measurements, to generate the entire shape of a seaworthy hull with nothing more than a rope and a batten. Cracking this code would be like discovering the lost chord progressions to an ancient song, allowing us to understand not just the notes they played, but the underlying harmony that made the music so powerful. This quest for knowledge now turns to the Earth, with the faint but thrilling possibility of a monumental discovery. The volcanic ash that buried the town of Herculaneum in 79 AD carbonized and preserved an entire library of papyrus scrolls in the so-called Villa of the Papyri. These scrolls, many of which remain unreadable until recently developed, technology can virtually unroll and decipher them, are a potential treasure trove of lost classical knowledge. While the library appears to be dominated by philosophical works, the possibility exists that other villas, yet to be excavated, could contain the personal papers of a wealthy shipowner or even a retired Navalese architectus. The dream of finding an actual manual, a De Re Navali to complement Vitruvius's De Architectura, drives archaeologists forward. Imagine a scroll containing diagrams of hull curves, notes on the ideal timber for different components, or even a ledger of costs for a specific ship. Such a find would be the Rosetta Stone for Roman maritime studies, transforming our understanding from informed reconstruction into direct conversation with the master builders themselves. These unanswered questions are not merely academic. They are what fuel the next generation of exploration. Every new shipwreck discovered by underwater archaeologists is a chance to test our theories and ask new questions. Advanced techniques like three-dimensional photogrammetry allow researchers to create perfect digital twins of a wreck on the seabed, studying it from every angle in the comfort of a laboratory. Chemical analysis of caulking materials can trace trade routes for tar and pitch. The study of tool marks on wood can even identify the work of individual craftsmen, offering a glimpse into the personal styles within a shipyard crew. The mystery of Roman shipbuilding is no longer a silent void, but an active, vibrant field of inquiry. Each new fragment of evidence, whether pulled from the sea or virtually unrolled from a carbonized scroll, adds another piece to the puzzle, reminding us that the dialogue with these ancient engineers is far from over. Their silent legacy continues to challenge and inspire, a testament to a level of ingenuity that we are still striving to fully comprehend. The story of Roman shipbuilding is far more than a historical curiosity. It is a profound testament to the boundless potential of human ingenuity when faced with immense challenges. It forces us to reconsider our modern definition of technology, which so often revolves around digital models and precise schematics. The Romans achieved feats of engineering that would be impressive even with today's tools, but they did so by mastering a different kind of intelligence, one rooted in deep, experiential knowledge, sophisticated rule-based systems, and craftsmanship elevated to an art form. They constructed a maritime empire not in spite of their lack of paper blueprints, but because they had perfected a system where the plans were more dynamic and more resilient than any drawing could ever be. The true blueprint was a living entity, encoded in the minds of the master shipwrights, embodied in the skilled movements of their hands, and reinforced by an industrial organization of staggering efficiency. This Roman approach highlights a crucial distinction between information and knowledge. We live in an age of abundant information, where instructions for almost anything are a quick search away. But the Roman shipwright possessed knowledge, a deep, tacit understanding that comes only from years of direct experience. He knew how a specific piece of oak would respond to the adze, how a hull curve would interact with a specific wave, not because he read it in a manual, but because he had felt it, seen it, and learned from it over a lifetime. This knowledge was stored in a living library, passed from master to apprentice through observation and practice. It was a system that valued the wisdom of the hand and the eye as much as the logic of the mind, creating a continuity of skill that ensured each new generation could build upon the successes and learn from the failures of the last. The legacy of these unnamed engineers extends far beyond the wrecks at the bottom of the Mediterranean. It serves as a powerful reminder that advanced technology is not solely defined by the complexity of our tools, but by the depth of our understanding. The most sophisticated computer-aided design software is useless without the human intuition to ask the right questions and interpret the results. The Romans teach us that innovation can flourish within a framework of proven principles and shared practices. Their rule of thumb proportions were not a limitation. They were a launchpad for consistency and rapid scaling, proving that standardization and quality are not mutually exclusive. In an era increasingly focused on automation and artificial intelligence, the Roman example brings us back to the irreplaceable value of human expertise, creativity, and the ability to solve complex problems with elegant, practical solutions. Ultimately, the silent shipyards of ancient Rome speak to us across the centuries with a compelling message. They remind us that the greatest structures, the most ambitious ventures, are built first and foremost on a foundation of knowledge and skill. The empire was connected and sustained by vessels that were conceived in the imagination of craftsmen and realized through their collective effort. This story challenges us to look beyond the blueprint and appreciate the profound intelligence embedded in tradition, in mentorship, and in the quiet confidence of a job well done. The true marvel is not that they built ships without blueprints, but that they built a system of knowledge so robust and so effective that it could conquer the sea itself, leaving behind a legacy not of parchment, but of timeless human achievement. So as the final plank was fitted and the last rope coiled, we're left to wonder what truly stands as the most breathtaking part of this entire endeavor. Was it the sheer organizational genius, the ability to coordinate hundreds of workers and tons of material, as if conducting a symphony of industry? Or was it the sublime artistry of the craftsmen, the individuals who could feel the perfect curve of a hull in the swing of an adze and the touch of their hand? It's a difficult choice because both were essential. One represented the mind of the empire, its capacity for large-scale, systematic thinking. The other represented its soul, the irreplaceable value of human skill, passed down through generations. I'm genuinely curious to hear which aspect amazes you more. Was it the system or the artistry? Let me know your thoughts down in the comments below. I love reading your perspectives. If uncovering these lost secrets of ancient engineering has captured your imagination, if you've enjoyed this journey into the noisy, sawdust-filled world of the Roman shipwright, then you won't want to miss what we explore next. Our channel is dedicated to unearthing history's greatest mysteries, from forgotten technologies to the untold stories of everyday life in the ancient world. Make sure to show your support by liking this video and subscribing to the channel. Your engagement is what makes these deep dives possible. Thank you so much for watching, and remember, sometimes the greatest plans, the most enduring and brilliant designs, are the ones you never need to draw. They are written in skill, in tradition, and in the timeless ingenuity of the human spirit.